logic instructions. In logic instructions, you can see operations like AND, OR, XOR, clear, complement, rotate, rotate with carry, swap, and NOR operation. So first, let's see the logic instruction, that is AND operation. This AND logically. The opcode for AND operation is ANL, that is AND logically. So it has different formats. Always the AND operation, OR operation, and XOR operation that happens between the accumulator register. So one of the operand will be in accumulator register, and also after the operation, logic operation is performed, after the logic operation is performed, the result also will be stored in the accumulator register. So example, ANL A comma hash 25 hex. So here you can see it is hash 25. Hash 25 means this 25 is data. So whatever the content in the accumulator register, it is ANDed with the immediate data 25. And the result will be stored in the accumulator register. So the operation that happens here is A and 25. That is A dot 25, whatever the value in A, if it is 10.25 is the operation that happens here, and the result will be stored in the accumulator register. So this operation logically ANDs the value of A register with the immediate data. So the immediate data is available in the instruction. This is an immediate addressing mode. So the data is immediately available in the instruction. So the content of A register is ANDed with the immediate data and stores the result in A register. Number of cycles required is 1. So AND is used to clear any bit. The alternate function of an AND gate is to clear any bit of a register. So if we want to clear any bit, we must AND it that particular bit with 0. So you know that when we AND a particular bit with 0, you will get the answer as 0. So you can write that 1.0, that is 1 and 0, the answer is 0. So but if we AND a particular bit with 1 and 1, you get the answer, that is 1. So when you AND a particular bit with 0, you get the answer 0. Or you can say 1.0.0 also, you get the answer 0. So when you AND a particular bit with 0, you get the answer 0. But when you AND a particular bit with 1, that is 1.1, you get the answer 1. And 0.1, you get the answer 0. So when you AND a particular bit with 0, you get the answer 0. But when you AND a particular bit with 1, you get the answer as it is. So this is the number, it is ANDed with 1, you get this number itself. And also 0, when you AND with 1, you get the number 0. So you can say that when we AND a particular bit with 0, you get the answer 0. And when you AND a particular bit with 1, you get the same number. If it is 1, you get the answer 1. If that bit was 0, you get the answer as 0. So this, the another alternate use of the AND gate is used to clear any bit of a register. Some registers are byte addressable registers, so we cannot change only a particular bit. We need to load the full byte of data with the new byte. So in if you want to clear a particular bit, one bit of a register, we can use AND operation, that is AND that particular bit with 0 and all other bits with 1. You can clear that particular bit alone in that register. So this is because if we AND anything that is 0 or 1 with 0, it becomes 0. But if we AND anything that is 0 or 1 with 1, it remains the same. So suppose we want to clear the lower nibble of A register. So if A register has a value 95, that is 951001 and 0101. So if you want to clear the lower nibble, that is the lower nibble is this, you want to clear it, this should be ANDed with 0 and this should remain the same. So this should be ANDed with 1. So you should AND this register with the number F0. So F0 is 111000. So when you AND this with 1 and 0, you get 0. When you AND bits with 0, you get the value 0. And if you AND bits with 1, you get the same number. So the result that is stored in A register will be 90. That is, the lower nibble of the A register gets cleared. Is it clear? So next, syntax of AND register, that is ANDing the accumulator register with a particular RAM register. So any RAM register can be ANDed with the accumulator register, that is ANL A, R0. The A register will get the answer A and R0. The content of R0 register and the content of A register get ANDed, and the result will be stored in A register. So logically ANDs the value of A register with the value of RAM register, stores the result in A register. Number of cycles required is 1. It is next is ANL A, address, that is direct addressing mode, then the ANL A, 25 hex. Here the 25 hex is the memory location. So if you put a hash before the 25, that means it's immediate data. Without hash, it means the memory location. So it is ANDing the content of A register with the content of the memory location 25 hex. So this gets ANDed and the result is stored in the A register. Number of cycles required is 1. It logically ANDs the value of A register with the content of the address. ANL A, @RP. This is indirect addressing. In indirect addressing, the register pointer is used. So an @ symbol comes, you know that it's indirect addressing. That means the register is act as a register pointer. Register pointer means whatever the value in this register. If R0 register contains 25, that means the AND operation is done between A register and the content of memory location 25. So from memory location 25, the value is taken and ANDed with the content of A register, and the result is stored in A register. So logically ANDs the value of A register with the content of the location pointed by the register. So the R0 register is pointing to a particular memory location. So from that location, the data is taken, and also data from the A register, it will AND operation is done, and the result is stored in A register. Number of cycles required is 1. Now here, ANL address, A. So here you can see the first one is a memory address and second one is the accumulator register. So here the operation is done between the content of 25 hex location and the accumulator register. But here the result is stored in the 25 hex memory location. So here you can see the first one is the destination. So where we stores the result. So 25 hex location is the destination. We do AND operation with 25 hex, the content of 25 hex memory location and the content in A register, and the result is stored in 25 hex memory location. So logically ANDs the content of address with the value of A register, stores the result at the address. Number of cycles required is 1. ANL address, #n. So here ANDing 25 hex with a direct value. Here this 25 hex means the location 25, and this is #30 means it's an immediate data 30. So the content of 25 hex location is ANDed with an immediate data 30, and the result is stored in 25 hex location. So logically ANDs the content of address with immediate data, stores the result at the address. It requires 2 cycles. Next is OR operation. OR operation can also have all these syntax, that is ORing with ORing the A accumulator register with an immediate value, that is A register or A, #25 hex. Here the content value of A register logically ORs with the content of 20, logically ORs with the direct value, immediate value 25 hex, and the result is stored in A register. So logically ORs the value of A register with the immediate data 25, and the result is stored in accumulator register. Number of cycles required is 1. So there is an alternate function for the OR operation. OR is used to set any particular bit of a register. We said that AND operation is used to clear a particular bit of a register. Here OR operation is used to set any particular bit of a register. So if we want to set any bit, we must OR the particular bit with 1 and the remaining bit with 0. This is because if we OR anything that is 0 or 1 with 1, it becomes 1. So, but if we OR 0 or 1 with 0, it remains the same. So, suppose if we want to set the lower nibble of A register, the lower nibble has the A register contains the value 95, that is lower nibble is 5. We need to set all the bits of the lower nibble. We OR the lower nibble with 1 and the higher nibble should remains the same. So we OR it with 0. So you get the result, that is 95. When we OR with 1, we get the answer 1. And if we OR with 0, we will get the number as it is. Number is the same. So 9F is the answer that we get at the accumulator register. So the lower nibble of the accumulator register is set. All the lower nibbles are set. Next index, that is ORL, A comma, a RAM register. Any RAM register can be used. It logically ORs the value of A register, ORL A comma R0, that is logically ORs the value of A register with the value of R0 register and stores the result in A register. So A register will get the result. The first one is the destination. So A register gets the result, A or R0. Number of cycles required is 1. So ORL A comma address, ORL A comma 25 hex, example, that is ORL A comma 25 hex. So here this 25 hex is a memory location 25. So it logically ORs the value of A register with the content of the location 25 hex and the result is stored in A register. So here it logically, the operation that is happening here, it is logically ORs the value of A register with the content of the address, which address that we are specifying here, and stores the value, the result in A register. Number of cycles required is 1. That is indirect addressing, ORL A comma at the rate RP. That is this act as a register pointer. Example, ORL A comma at the rate R0. So here logically ORs the value of A register with the content of the location pointed by the register R0. So the R0 register contains some value, maybe a 30. That 30 means it is pointing to the memory location 30 of the internal RAM. So from internal RAM location 30, you get the data. It is ORed with value in A register and the result is stored in A register. So number of cycles is 1. ORL address comma A. So ORL 25 hex comma A, that is 25 hex is the address location. So ANDing or ORing the data in 25 hex location and the value in A register, and the result will be stored in 25 hex. So first one is the destination. So the result here will be stored in 25 hex location. Logically ORs the content of address with the value of A register. Stores the result at the address location. Number of cycles required is 1. Or logically the memory location with an immediate data. So or logical 25 hex hash 30 hex. So here hash 30 hex means it's immediate data. Without hash, it is the memory location. So or logically the content of the address with the immediate data, and the result is stored in at the address location. So number of cycles required is 2. Next is XOR operation. XOR logically, it is XRL, XOR logically. XRL A comma hash N. So the A will get the result is stored in A register. It XORs the value in A with the immediate data 25. So logically ORs the value of A register with the immediate data and stores the result in A register. So XOR operation is also having an alternate function. That is, XOR is used to complement any bit of a register. So we have complement instruction. Without using the complement instruction, if we need to do complement, you can do with XOR operation. So if you want to complement any bit, we must XOR that bit with 1 and the remaining bit with 0. This is because if you XOR any bit that is 0 or 1 with 1, it gets complemented. But if we XOR any bit that is 0 or 1 with 0, it remains the same. Suppose if you want to complement the lower nibble of A, assume A register has the value 95 hex, that is 1001 0101. So we need to complement the lower nibble. So to complement the lower nibble, we are XORing the lower nibble with 1 and the higher nibble should remain the same. So we are XORing the higher nibble with 0. So XOR the register with the number 0F. As a result, A will remains 9. A will becomes the lower nibble remains the same and the higher nibble is complemented. So 0101 becomes 1010. So you get the answer 9A in A register. All the syntax that we discussed for and or logical and logical or operation is available for XOR operation also. XRL A comma R0. This is XORing between A register and the RAM register. Any RAM register can be used. Here it's example R0. So A and R0, A XOR R0, and the result is stored in A register. So here XOR with an address, direct addressing mode. So A register value is XORed with the content of the memory location 25 hex, and the result is stored in A register. This is A XOR logically A comma at the rate RP. The RP, that is register pointer, here A XRL A comma at the rate R0. Here logically XORs the value of A register with the content of the location pointed by the register R0. And the result is stored in register A. XRL A address comma A. Here the XOR operation happens between the location 25 hex and the value in A register, and the result is stored in 25 hex memory location. So logically the content of address with the value of A register stores the result at the address. So XRL address comma hash N. XRL 25 hex comma hash 30. Here hash 30 is the direct, the immediate value, and this is the direct address of the memory location. So the content of 25 hex is XORed with the value 30, and the result is stored in 25 hex memory location. So next is complement instruction, CPLA, that is complement A. CPLA, that is A gets one's complement of A. So whatever the value in A, it gets complement and it is stored in A register. So it's just like a NOT gate. Complement CPL is used as a NOT operation. If we do complement after NAND, we get it like work like as NAND. Complement after OR, it works like the NOR, and complement after XOR, it works like XNOR. So clear A, that is clear the content of A register. Whatever the content in A register, it is cleared to 00 hex. Clear the entire A register and makes it 00 hex. Swap A means the lower nibble and the higher nibble is exchanged. So swap A means whatever the value in A register, the lower nibble and higher nibble will get exchanged. If previously the content of A register is if A register the value is 65, so after swap A instruction, the A register will get the value 56. That is 56. That is the lower nibble and the higher nibble is exchanged. 65 hex means 6 is so when we swap, the lower nibble and the higher nibble got exchanged. That is swap instruction. It interchanges the nibbles of A register. If A register was 35, it will become 53. Another example, that is 35, it becomes 53. It is as good as rotating A register 4 times. 4 times number rotate ചെയ്താൽ we will get the same. No operation, NOP, it simply, PC simply becomes PC plus 1. There is nothing happens. This instruction performs no operation. It is typically used to produce a delay. Number of cycles required is 1. 1 cycle is delayed if you perform a no operation. If you want 10 cycles delay, we can do no operation 10 times like that. And you can use this no operation to generate delay. So next is the rotate instructions. Rotate instructions, we have 2 types of rotate instruction. Rotate left, rotate and rotate with carry. So rotate left means we are rotating all the bits to left by 1 bit position. And when we rotate left, the MSB goes to LSB. So that is the rotation. If you're rotating a bit, you can write so this is the number. If you rotate this number, we rotate this number to left, that is towards this side, every bit moves 1 position to the left. So this bit moves 1 position to the left, then it enters the carry flag. So every bit is rotated 1 bit position to the left, and this bit that is coming out of the MSB bit that goes to the LSB. So MSB in the out bit in LSB load. This is the bit that is going out of this bit. That is the rotation happening here. So every bit is shifted 1 bit position to the left, and the MSB bit goes to the LSB. That is the rotation. So every bit is rotated. Also, a copy of this bit goes to the carry flag. So also this here, this 1 bit that goes to 2 places. That is, this goes to the carry and also to the LSB. So this bit goes to 2 places. All bits are shifted to left by 1 bit position, and also the MSB bit goes to the carry flag. So every bit is shifted to left by 1 position, and the MSB bit goes to LSB and also to the carry flag. That is rotate left. Let me explain the rotate left with carry. So here rotate left with carry. Rotate left with carry means if you have the carry is also included in the rotation. So if you have an initial carry, if it is 0, so this carry is also included in the rotation. So here you let's assume that you have an initial carry that is 0. So MSB bit goes to the carry flag and the carry that goes to the LSB. So here carry will be going to the LSB. Every bit is shifted by one position. So here it is 1, 1, 0, 0, 1, 0, 1, 0. And here the carry comes to the LSB. So you get the answer like this. That is carry is coming to LSB and all other bits are shifted to left by 1 bit position. Here the carry is also included in the rotation. Is it clear? It is here rotating with the help of carry. In previous case, we didn't rotated the carry, but a copy of the MSB goes to carry flag as well as to LSB. But here the carry is also included in the rotation. That is all the bits are left shifted to left and the carry flag is taken to the LSB. Earlier case, that is rotate without carry means the MSB goes to LSB. If you are rotating with carry, that is carry will be going to the MSB. Carry is also included in the rotation. That is 9 bits we are rotating. Previous case, that is rotate without carry, RLC. Rotate left RL, comma A means the accumulator register is rotated without the carry. That is MSB goes to LSB. Only 8-bit rotation is happening there. But the MSB also, a copy of MSB goes to carry flag also. But here, the carry is also included in the rotation. The carry goes to LSB and all the bits are shifted to left. MSB goes to carry flag. So here it rotates a register in left direction by 1 position along with the carry flag. Each bit goes to 1 position to the left. MSB goes to carry flag goes to LSB. That is rotate left and rotate right. Rotate left, rotate are all used to determine the value of any bit in a register. So rotation happens in a register. To know the value of a bit, rotate the register as many times so that the bit comes into the carry flag. Okay, the bit for first bit, MSB bit angle, just rotate 1 time. If you want to check this bit, we will rotate 4 times to get that bit in the carry flag. Now check the carry flag to know if your desired bit was 0 or 1. So next is rotate right, RR, that is rotate right for accumulator register. So RRA, that is a register will get the value a register rotated right by 1 position. So here we show the rotate left. So here we have a carry flag, a carry bit. Let it be. So if this is the number in accumulator register, every bit is shifted to right by rotate the bits of a register in the right direction by 1 position. So every bit will be rotated to the right. So what happens here? Here we don't rotate the carry flag. This is rotation without the carry. So every bit is rotated to right, and this LSB comes to the MSB bit. So carry a copy of it is gone to carry flag also, and to the MSB bit. So this LSB comes to carry flag and also to the MSB, and all other bits are rotated by one bit, right by one bit position. So this will be the answer after rotating one time. That is, every bit is shifted to right by one bit position. So this bit, you can see, the first bit is rotated to right. Every bit is rotated to right by one bit position. And this LSB that is going out of the it goes to two position, that is to MSB and also to the carry flag. So this is rotate right. Rotate right means every bit in A register rotates the bits of A register in the right direction by one position, and each bit goes one position to the right. LSB bit goes to the carry flag as well as to MSB. So this records one cycle. And let's see what is rotate right with carry. With carry means the carry is also included in the rotation. So here, so you can see this. So here, rotate right with carry. The carry is also included in the rotation. So rotates the bits of A register in right direction by one position along with the carry flag. So each bit goes to one position to the right. The LSB goes to the carry flag and the carry flag goes to the MSB. So here LSB goes to carry flag and here the carry flag is going to MSB. So this one is going to the MSB. We can write it as. So here the carry, that is LSB, is going to the carry flag. So the carry flag will get the value 0. And the carry bit is going to MSB, that is 1 here. You can write 1. And every other bits are shifted by one position. So after rotation, you'll get the answer like this. Every bit will be shifted. The LSB goes to carry goes to MSB, and every bit is shifted to left by one bit position, that is rotate with carry. The carry is also included in the rotation. So that's it.